Our first speaker is Dr. Wolfgang Kerzendorf. He's an ESO fellow, where he started there in 2014. And before that, he was a postdoc fellow at the University of Toronto. And Wolfgang finished his thesis titled Type 1 Supernovae, Progenitors and Explosions in 2011 at the Australian National University. And his research focused on stars before and during and after the explosion. So today he's going to talk about what ignites white dwarf.
Thank you very much. Oh wow, voice is very loud. Thank you very much for giving me the opportunity to talk here, and I'd specifically like to thank Grauer and Lorenzo, who sort of made this possible and arranged everything, and for me to come here and give that talk. And as with all my talks, I like audience participation. For me, it's much more interesting if people ask questions during the talk and if there's a wild discussion going, rather than me giving a monologue for 20 minutes. So please, jump in if you have any questions or have any comments. So I always love to start with this picture, and here it's a particular pleasure because this picture is of SN 9094D, Type 1a supernova, and this picture was put together by CFA's own Pete Chalice. So I think that's a very nice showing why I think supernova are cool. I guess I don't need to tell this to the high energy folks here because we're all interested in supernova or in high energy explosions. So what makes a Type 1a supernova? So what we do know is it doesn't have hydrogen, and I guess that is sort of one hint, and has radioactive decay of nickel-56 and then cobalt-56. That very clearly says it must be burning in degenerate CO matter, and then it also very clearly says probably it must be the explosion of a thermonuclear explosion of a white dwarf. There's not much else in the universe that has degenerate CO matter and doesn't show hydrogen, I would say. So the main question is, how do we ignite one of these things? Because they're inert. Theoretically, they don't really ignite. And I think a really nice graph showing what you need to do to make the thing explode is from Martin van Kerkwijk in 2011. And essentially it shows density versus temperature. And it shows a cooling timescale. So you have the neutrino cooling, the cooling and heating timescale. So you have the neutrino cooling timescale and the carbon-carbon burning heating timescale. And so if you're slower than this, you have stable burning. If you're faster than this, you have a runaway explosion. So what you need to do with a white dwarf, before we go into any explosion scenarios and binary scenarios, you need to bring a white dwarf from here to here. There are many scenarios by now, and the reason why there's many scenarios is because we haven't really figured things out yet. There's the accretion scenario. Some people call it a single degenerate scenario, but because there's one degenerate white dwarf and a non-evolved or evolved star that is not a degenerate star. But I mean, I'm going to call the accretion scenario, and that will be clear in a while. So what we have is we have our white dwarfs, and essentially if you invert this and convert this to mass versus density, when you go up close to the Chandrasekhar limit, not at the Chandrasekhar limit, you're going to cross this region where you have runaway carbon-carbon process. So essentially you cross 3 times 10 to the 9 grams per cubic centimeter, and as we saw in the diagram before, this is the line where you have the runaway starting. So one of the ways to do this is feed the white dwarf enough mass until it crosses this line, and then we have the runaway going. So you have slow accretion and then the runaway here. The other scenario, another accretion scenario that also works maybe with a star, but it also might work with a white dwarf, is the double detonation accretion scenario, where essentially what you do, you accrete mass onto the white dwarf, and you accrete helium mass onto the white dwarf, and you ignite the helium mass. The helium burns around the white dwarf, sends shock waves into the core, and then compresses the core to also go up to the densities and temperatures required for ignition. And then we have sort of the classic double degenerate scenario, where you have two white dwarfs. I'm going to call the merger scenario, and the reason of this will also become clear in a second, where you have two degenerate CO white dwarfs. And I mean, they merge and they ignite. And there's some ideas of how to ignite them. One of them is the violent merger. But essentially, during the merging process, you reach high enough temperatures and you explode the whole thing. One of the problems with this scenario seems to be that it might not make very spherical explosions, and for all we know, 1As have very low polarization and seemingly are very spherical objects. So here we have the explosion. So here we cross this line going from merger and then having a runaway process again.
But that scenario must happen sometimes, right? And it must be that there are such white dwarfs and they do merge.
Yes, I mean, all in all, like, I mean, as we've had very nicely demonstrated by LIGO, things go together after a long, long time. So I think all of them must merge. The question is, during the merger, do you have the conditions to ignite them? So Nomoto et al. 1982, and let's see if I get the scenario together, suggested that when you merge, you burn to oxygen neon and then you collapse. You do an accretion-induced collapse and you make a neutron star. You don't make a 1A. So that is one possibility. But yeah, all of them must merge at some stage. There are several merger scenarios. We have the violent merger. We can also have collisions. Rosberg et al., for example, suggests this. Or we could merge, in the envelope of a red giant. So you essentially have this merger in the envelope and then you detonate. And this all gives sort of different observational signatures. And this brings me to the title slide of this rather long introduction. I'm an ESO fellow, and I'm going to talk about why white dwarfs explode. To just sort of give a brief overview of what the theoretical and the observational states are, is we have, first of all, the progenitor system, and that's what we are sort of trying to think about, like, what makes them explode. Then we have the explosion itself, which takes, less than 100 seconds, and we can only model this. Then we have light curve and spectra, and last but not least, we have the remnants. And so the idea is to sort of tie all of this together to make a consistent story, and we need to think about if 1As are a consistent story or if there are multiple stories to this theme. And I normally really enjoy this paradigm of trying to understand the scenarios. Eliminate whatever is impossible and whatever remains, no matter how improbable, probably is the truth. So during the talk, I'll try to use this as a guide. So the case of surviving companions. So that's one nice prediction that the accretion scenario has. You need to have something that's left over. And that's why I called them accretors and mergers, not single degenerate and double degenerate. So in the accretion scenario, something must survive in most cases. And for the merger, it is a merger, so there's nothing left over. And this has been the bane of my existence for a while now. So people have sort of looked at this to see what happens to a companion. And I'm going to show here what would happen to a companion that's a main sequence companion. So we have the exploding white dwarf, and we have the companion. This is a study by Pakmo et al. 2008, because I found the video from this, but there's other studies as well. And you essentially have this explosion here, and you can sort of see that the star has ruffled feathers, but does not get disrupted. So you should find this. To sort of use another thing to show more in detail what happens, I'm going to go to the Marietta et al. Study. So essentially you can see the the star, the shock wave hitting the companion. You see bow shocks happening. And in these bow shocks, they get very hot, and that's one prediction by Kerzendorf et al. 2010, which has temperatures greater than 10 to the 5 Kelvin. So if you're looking in the right direction, that's what you might see. Most supernovae, most 1As do not show this. There's some that have UV excess, whatever that means. So this is, I think, an interesting prediction of this. We drive a shock through the stellar core, so we heat that up. For some supernova, this is probably more for type 2s, but I mean, I'm going to mention this here anyways. There might be material in the remnant from the star, and you might be able to find this. We have never found this in any of the 1A remnants that we know about. And some suggest, I mean, that you might find some sort of cone or something left over. But if you evolve this long enough, it seems to close off. So in remnants, that's not a signature you can find.
I just wanted to comment, Wolfgang, something
Go ahead.
you know yourself very well, I think, which is that, in the accretion scenario where it's a main sequence star,
Yeah.
you only get high enough accretion rates when the main sequence star is comparable to or more massive than the white dwarf. So you go through a period where the accretions can, in fact, grow the white dwarf. And when the mass ratio changes,
Yeah.
you're not really growing the white dwarf. In fact, you're creating what could be eventually a CV. So now the question is, when does the explosion occur versus when this main sequence star continues to evolve?
That's,
And so
yeah.
even without spin up, spin down, there's a question about that. But if it's possible, and I think there are now some nice calculations from Wheeler and others that have explored the spin up, spin down scenario in more detail. If you spun up during accretion, the spin down can take enough time that in this scenario you're left with a different kind of main sequence star, perhaps even a brown dwarf-like object at the end.
So you mentioning the accretion thing is very good, because one of the observational evidences that we seem to have is that when you accrete, you would emit X-rays, and we do not see enough X-rays in elliptical galaxies. I think that was the statement. As well as the study last year that sort of showed if you would have this high flux, UV X-ray flux, you would ionize a medium, and that would recombine, and around supernova remnants you should see this, which was a tycho last year, I think, disproven. So essentially, there doesn't seem to be a lot of accretion happening, as far as I understand.
I think what we know is that there are a lot of accreting white dwarfs. There have to be, because CVs require them. The fact that we
Yeah.
have CVs means that there's other populations of somewhat more massive main sequence stars that are also providing mass. But we don't see them. You're absolutely right that we don't see them at X-ray wavelengths
Yeah.
or at extreme UV. That doesn't mean that they don't exist.
No.
It just means that they're not emitting at those wavelengths.
No. And I mean, the question is, are those linked then to 1As?
That's right. We don't know. I don't know the answer to that
No.
question, but I'm just saying that these types of arguments, you have to make them, but there are caveats that are
Yeah.
extremely important to them.
Yeah, maybe I should have preempted my talk with. I'm going to present a lot of questions, not a lot of answers. I apologize for that.
Question. What do you base the prediction of the expected X-rays from the accretion?
Well, I mean, if you burn material at the surface, if you have nuclear burning at the surface, I would think that you see those X-rays. So hydrogen to helium conversion.
Like how much of it?
I'm not an expert, but I think there might be experts in the room.
Well, it will depend how the accretion is done. Whether you have an overflow and dumping a lot or little, or
Probably shouldn't take all this time, but
Well, if people are interested in this.
it's a lot of X-rays, and you can look at some of them book 2011 or something. It's a lot of X-rays, and most of the X-rays which should be observable come from the point where the white dwarf reaches 1.2 solar masses, between 1.2 and until it reaches Cherenkov solar mass. Then it really emits a lot of X-rays, and unless something miraculous happens, it should be observable.
the white dwarf, not the
The
accretion.
steady slow burning white dwarf, yes.
Well, that's the theory as it was understood in the 1990s.
Right.
But we now know
Good. Well, I'm going to jump ahead, as there's lots of discussion I see, and maybe we can split off afterwards and have this. Nope. No, it doesn't want to go. I mean, no. Technology. That is interesting. Sorry. So anyways, what we should have is a surviving companion. I mean, no. If we have the classic sort of single degenerate scenario with a red giant or a main sequence star. A couple of us have looked in ancient remnants for these single degenerate companions or for these accretion companions, because I think that is the prediction that the scenario makes. And for now, we've been rather unsuccessful. So we have looked in 1006 for main sequence and red giant companions. We've looked very, very closely in Tycho for any of those. And there are many people that have looked, but I mean, we've never found a consistent companion that seems to fulfill all the requirements. We've looked in Kepler, and also there's nothing bright in there. Specifically because there's a study that suggests it's a wind-blown bubble, and so you would expect a red giant there that would be very bright. But there's not even a very bright star in Kepler. So all of this is rather unfortunate. So the typical prediction that we have from the single degenerate scenario, which is in most textbooks, doesn't seem to hold. One of the things that people have come up with is how about we have, instead of main sequence or red giant companion, we have a helium white dwarf, especially in the accretion scenario where you accrete helium and then you ignite the white dwarf. And I have this wonderful movie that I think is really, really cool that sort of shows this. And then I'm going to talk about the companion. So this is a movie by Rüdiger Packmore, and Ken Shen and many others have sort of worked on this scenario. And that would work. You would accrete and you would have a surviving companion, but it would be explained that we never find this one because essentially it's a white dwarf. And so you can see, like, the explosion running around the white dwarfs, compressing the white dwarf, and then the white dwarf explodes, which I think is very nice. So Ken Shen and Josiah Schwab in 2017 then made calculations of what such a helium white dwarf would look like, and they suggest that it would be hot because it's sort of shortly after the explosions, and it would have a delayed nickel decay because it's starved of electrons. And so what we did is we looked for surviving white dwarfs, and the only remnant where you can easily do this, and a mini sigma outlier in this case of the remnants in general, lies above the disk and is not very heavily extincted, and so you can go there and you can look there. So that's one thing that's very, very recent. We've looked for these companions. We looked in the circle. Actually, this is a little bit outdated. After the first referee report, we enlarged the circle and looked for anything blue in there. So these are the Shannon-Schwab 2017 models. And as you can see, there's nothing that's bright enough and blue enough. The other thing that you can do is you can say, well, I mean, no, if you look for white dwarfs, what kind of white dwarfs would be in there? What kind of general white dwarfs? Maybe the models are wrong. And so we can put the cooling models for white dwarfs in there, combine this with a smart likelihood, and then we can see we essentially do not find any young white dwarfs. So in this remnant, in this big circle, there are no white dwarfs that are younger than 10 to the 8 years old. So if there are any, they must have cooled, and so they can't have been very close to the explosion. So after this, Ken Shen was a little bit disheartened, and he said, well, I mean, no, this scenario, we have this thing, this helium white dwarf flying off, like, no, it doesn't seem to work. But he said, well, I mean, the Gaia data release 2 is around the corner, and that's why I've been working in the past week. Because what we have done is we looked for fast-moving white dwarfs in 1 kiloparsecs or 2 kiloparsecs around us in the Gaia data release 2. And so we found 3 of them. They move at extremely high galactocentric velocities. They are definitely seemingly unbound. And this is essentially hot off the press. They also lie. I mean, the three candidates here, and there's another one that was discovered before, lie in a weird region of the parameter space. They're pretty red, so we wouldn't have detected them in our search in the 1006 remnant. But I mean, they're weird and they have spectra that are seemingly similar. So this is very new. We found a group of, we looked for fast-moving, weird white dwarfs, and we found them, but that doesn't mean that they're the 1A progenitors. But I think this is a very interesting evidence. So, to summarize, they don't seem to have bright survivors, 1As. We've scoured 10 remnants, and I listed only a few. There's been also work going on in the LMC and SMC to look for them, and we never found anything there. And I always said until last week, sort of, it points to mergers. But I mean, the new, very new data might suggest that actually we just missed them, that they're actually accretors. But I mean, that we missed them. And that's also our old statement where I say Gaia will help. But I mean, and now we have first results from Shen et al. 2018, and we're working on feverishly on more. And I think there's some very interesting things to come. And I think this is the end of my talk. Now the mouse is gone. This is all great. Sorry. I don't know. Today is not. Anyways, this is the end of my talk, and I mean, essentially, we still have no clear understanding how we ignite white dwarfs, and I think I'm going to open for more questions. There are. If I had a mouse, unfortunately this, the mouse is here. Shen et al. 2018, there are spectra. They look unusual. I mean, I don't know if I can bring that up. Let me just mirror this, then we can. These are the spectra. They're very, very bright. They're like hundreds of the sun, probably. Hundreds of the luminosity of the sun. So they're much, much brighter than normal white dwarfs. And, yeah.
Helium white dwarfs?
I don't think they show helium lines. I mean, there have been many discussions going on currently, and yeah. But I mean, I encourage you to look at this paper. So you had a question?
Yeah, I was just wondering, you must assume, I mean, these things have velocities of 1,000 or so kilometers a second. You must make some assumption about the velocity of the remnant when you do your searches.
So, yes, I mean, for most remnants do not show a very excessive velocity. I mean, the problem is when you measure velocities of something that expands at 1,000 kilometers per second, it's difficult to sort of measure intrinsic velocity of a few hundred kilometers per second. There is one remnant, Kepler, which moves at a systemic velocity seemingly of 180 kilometers per second, and is a little bit out of the disk. Not as far as 1006, but I mean, it is interesting. So that's one of the things when I looked in the Kepler remnant, I'd hoped that you would also find, in addition to the 180 kilometers per second, I mean, no, it would actually give you more signal if there was a companion in there. But specifically for Kepler, which moves, there also seems to be the theory that it was exploded in sort of a common envelope, where you would suggest it was an AGB star as a companion, and that would be very, very bright post-explosion. But there's not even a very bright star in there.
Do you actually know that those historical supernovae are 1As?
So for Tycho, we know for Tycho we know this. We have light echo. For both 1006 and Kepler, we have very good X-ray spectroscopy where we see lots of iron, and that seemingly, I don't know colors, but then this is someone who has been working on this a lot, and he assures me that they look very, very similar. And if you think that Tycho, Tycho definitely was a 1A, then the other ones are also likely 1As. There's one more remnant called RCW86, which is likely the explosion, which is likely linked to SN185, the first recorded supernova, and that is a little bit unusual, a little bit different, and but it's probably 1A as well. Good. Thank you.
He'll be in B234 most of the time. You can also email him.
That's fine. I want the other one.
Our second speaker is Dr. David Barnett. And David started physics at the University of Warwick before completing his PhD at the University of College London. And in 2014, he joined the University of Manchester as a postdoc. And he moved to MIT last year. And today he's going to talk about explosions of formation and destruction of cool core with illustrated PhD.
Thank you. Yeah, so those of you who don't know me, I'm David Barnes. I'm a postdoc at MIT. This work is mainly being done with Mark and Mike, who are both at MIT, and Raoul, who's in the crowd and here at CFA, and the illustrious TNG team, which includes Lars Hernquist and Federico Marinacci, who are both here as well. So basically, we're going to look at cool cores in simulations, fundamentally. So this is probably slightly redundant as a slide here, but what is a cool core? And so cool cores are basically galaxy clusters that have very bright X-rays in their center, in their core. And when you look at the gas cooling time based off their X-ray luminosity, the cooling time there is shorter than the Hubble time. And when you measure a temperature in the core of these objects, then they've got sort of typical temperatures that's about a third of their virial temperature, hence the name cool core. And cool cores are also associated with more relaxed morphologies. So this is a plot here from Mance 2014. On the left, we have a cool core cluster. So you can see this very sort of sharp peak in the X-rays in the center. You can see it looks fairly relaxed. And on the right here, we have a non-cool core cluster where you don't see this bright peak, and it's sort of more extended and more elliptical in its shape rather than sort of circular. And so before the launch of sort of XMM and Chandra, it was thought that there should be cooling flows in the middle of these things, but there aren't. And so that implies there's some kind of central heating source like an AGN. And so there are many, many ways of defining a cool core. So this is just, don't worry, you're not meant to be able to read this, but this is basically just a plot from Hudson 2010. And this is 16 different ways of defining cool cores and non-cool cores based only off X-ray data. And so you can go into optical data and various other formats and find other ways. So there are many ways of defining a cool core. And when simulations look at this, most of them just pick one. But in this study, we decided to actually do this properly, and we took 6. And so we're taking just basically a measure of the central electron number density in the middle, measure the sort of cooling time, a more classical approach to cool cores, the entropy excess from fitting. Now this is obviously, this method has some controversy around it from the Cavignolo sort of data, but we're using it because we're using the Cavignolo data, so we're just going to compare like with like. The concentration parameter, which is basically just a measure of the sort of X-rays. So it's a measure of the X-rays in the core as against a measure of the X-rays from the sort of larger cluster volume. In the physical case, the apertures that you're measuring it within are sort of 40 and 400 kiloparsecs. And in the scale case, we're scaling it by R500, so it's 0.15 and 1 R500. And then finally, the customers parameter, which is just basically the gradient of the density. And traditionally, for simulations, getting a cool core or getting anywhere near the cool core fraction has been very challenging. This has changed recently for one particular simulation, but it's still not obvious that simulations can definitely reproduce these. And so I'm going to start by just sort of going through illustrious TNG for a bit. And so this is a set of simulations that the first results came out last July, so there were 5 papers back then. And so there are 3 volumes. There's the sort of 100 megaparsecs, which is basically just the original illustrious volume, but done with the new retuned illustrious TNG model. There's this 300 megaparsec volume, which is great for studying sort of cluster physics and things like this. And so that's the one we're going to focus on today. And then there's the TNG 50, where the first papers are sort of in production for high redshift, but the simulation hasn't actually finished yet. But there will be papers on that probably sometime over the summer or in the fall. And so what we do is we take this 300 box, and we basically just do a mass cut at every redshift, and we take every object with a mass greater than 10 to the 13.75. And at redshift 0, this gives us 370 objects. And when we go to redshift 2, this gives us something like 10 objects. And you'll see why that becomes important later on. So I'm going to go through some of the gory details of the simulation for those that are interested, but for those that aren't, you can just watch the video. And so basically, what we're doing here is just following a patch of the 100 box here in this case. And in the top top left corner from how you're looking at it, you just got the dark matter, and you can see the structure forming is under gravity. And also, you also got the gas density as well there. You can see that the structure collapses. We form stars using the normal numerical simulations for these prescriptions. We have updated metallicity from our supernovae production. And so this sort of green plot here, you can see the metals as they start to spread through the box by pollution, and then they're kicked out by AGN feedback in supernovae. And so you can see this here. You can see the gas outflows that are coming out of these sort of collapsed structures, and that's what's causing the metals to go out. Also, in illustrious TNG, we now follow the magnetic fields. So that's what's shown in this top panel up here. And so you can see in the sort of collapsed structures, you can see the formation of sort of micro-Gauss magnetic fields. And you can also see that some of this magnetic field is being, again, kicked out into the surrounding structure by feedback processes. And so basically, illustrious TNG is the first sort of simulation that has this kind of volume where you can study clusters, but also has this sort of range of physics that's missing from a lot of other simulations. And so this is quite a long movie, so I'm going to cut it off. But what we do now is just basically look at the cool core criteria that we just defined on the previous couple of slides and see what they look like. And so that's what you get here. So again, to go through the panels, so the top left panel is just the central electron density, cooling time, central entropy, excess, and then on the bottom we have the concentration parameter within physical and scale apertures, and then we have the cuspiness parameter on the bottom right panel there. And so you can see, the first thing you notice is that actually there's no sort of bimodal distribution, it's all one continuous thing. And so when we take our criteria cuts, which are the black dashed lines in this case, we're basically just thresholding this distribution for cool cores. I'm sorry, no, that's the mass bins. So the blue triangles are cool cores, the black squares are sort of moderate cool cores, and then the red ones are non-cool cores. And so there's no real, with the exception of the scale concentration parameter, and I'll come back to why that looks like that towards the end, we don't see any mass dependence. What is mass dependent is the scatter. So if I just take the cuspiness parameter down here, you can see that there's much more scatter in the low mass end than there is in the high mass end. And so our cool core fraction, when you start breaking it into mass bins, varies with mass. But the actual distributions themselves are fairly independent of mass.
Can you say one more word about how
Sure.
you do some of the analysis?
Sure.
So for example, the density, for example.
Yes.
How do you define the center? How do you get the central density?
Okay, yeah, sure. So in all cases, we use the potential minimum as the center of the cluster. And when we, in a second, when I show some comparisons of observational data, we take the X-ray peak as the center of our cluster. So for relaxed clusters, that should be a reasonable sort of match. And cool cores are generally thought to form in more relaxed objects. So we're using that as our sort of comparison. And in terms of getting the central density, in this case, we're just averaging the density within the usual observational apertures. So we're using 1% of R500 in this case.
And the minimum of the potential is defined on a pretty small scale?
Yeah, so...
Galaxy is, for example, suppose there are two galaxies that are merging. Or two subclusters that are merging.
Yeah.
Each one has a bright galaxy in the center. Would you pick one of those centers, or would you pick the center somewhere else?
No, we'd pick one of those centers. So So in merging cases, yeah, you would end up picking one of those bright galaxies basically, because that's where the potential minimum should be. And so for a lot of these, we're just using the sort of raw particle data. But we've also done all of this with our Mach X-ray pipeline and trying to do things in a similar way. And actually, it doesn't really make much of a difference. for a lot of this. And then when it comes to the sort of concentration parameters, we're basically just measuring the X-ray luminosity that comes off these objects and taking the ratios. So yeah, so basically all of this is being done with the particle data, but you can do it with the mock X-ray pipeline that we have, but it doesn't really make any difference here.
So David, the values, the splitting values are what? From the Hudson paper or?
Yeah, so it depends on the criteria. So a lot of them come from the Hudson paper, and will be traditional Hudson paper values. For example, for the central entropy excess, we're taking the same values as Carvignolo, and how they split theirs into cool cores, non-cool cores. So in this paper, we give all the gory details about exactly what selection we make for our cool core, non-cool core splits. But yeah, so that'll change the fraction slightly. But we're always using because we have Mike, so we have access to most of the SPT data. We're always making the same cuts in the observations as we make in the simulations, so that we're always consistent. And for Carvignolo, they were handily enough published all of the actual raw values they got, so we can always make the same cuts. And so, in general, it's not given on this slide particularly well, but basically we slightly underpredict the cool cores. It depends on the criteria, and it depends on what mass range you decide to select. In general, because we're using SPT clusters for a lot of our analysis, a lot of it is very high mass clusters, and so we take a high mass sample, as I'll show on the next slide, and you get a better comparison in some cases and a worse comparison in others. So yeah, so low redshift we underpredict, which is shown on this slide here. So as I said, this is all 370 clusters at redshift 0 here, and in this case we're taking high mass clusters only. So this is 2 times 10 to the 14, and so that'll be 10 to the 13.75 on the left panel. And you can see that at low redshift, for example, here we're looking at the central density, and we underpredict by quite a large fraction. But if you go to the high mass, then you get sort of back up towards where the observations are. But the key point from this plot to take away is that even if you get this correct, you're still getting the redshift evolution wrong. And so with the advent of sort of SPT and Planck and things like this, you can now go and look at this as a function of redshift. And so the observations are relatively flat. But in this particular case, we find a much steeper relation. And this is true for any of our criteria. So if we go to the central cooling time here, for example, then again, you can see it's too steep, basically. So the dashed dot purple line is the observations, and the solid purple is the simulations. And so again, I come back to the mass dependence. Because we're using a high mass set of clusters as our observations, which is shown on the left plot here. So this is just basically a plot of mass and redshift for the observations in red and the simulations in blue. So you can see that these clusters are much more massive in the observations, and this can potentially cause you problems. And so we looked at this, and what you can do basically is use the same redshift bins as the observations, and basically just bin up your clusters, and then essentially match them by mass as a function of redshift. And so here you've got histograms basically of the clusters. So blue is the observations, and the red sort of dashed is our simulations. So they're perfectly matched in mass and redshift space here now. And we can look at the evolution again. And when we do that, we get this plot here. And so the blue line is our now matched sample for the simulations, and the red solid line again is the observations. And so you can see that the observations are still relatively flat, and they drop off at high redshift again. But the simulations are still sort of too steep, essentially, in their evolution. And the reason why this simulation evolution plot is so noisy is because we're oversampling our clusters. So we actually don't have a huge number of clusters that match. So for example, in this redshift 0.25 bin that we're looking at here, this sort of purple cluster, which is just one cluster, is picked sort of basically a third of the times. And so this happens, this one, and the orange one all happen to be non-cool clusters, and so you end up getting a fraction less than 10%.
So if I only went out to redshift of 0.8, would you say that was agreement, given the noise between the blue and the red?
Possibly, yeah. But yeah, again, so the limited statistics, because the volume of the simulation, although it's much bigger than any previous simulation, is still not massive. And so we don't have a huge number of these high mass clusters.
Just from the picture?
Yeah, just from the picture, you'd see a reasonable agreement there, yeah. But again, you can resample the clusters and you would probably get a very different evolution because of the oversampling issue. It's just the fact that we happen to have picked these ones that you get a reasonable match. And so why don't you quite get cool cores in simulations? So even though we get a reasonable match to some fractions, we're clearly getting the redshift evolution iffy at best. And basically it all comes back to AGN feedback. So what I'm showing here is the gas fraction, cumulative gas fraction, as a function of radius. The purple line is for the simulated clusters, and the grey sort of band is from the Rexess sample. And so you can see that the shape is just basically wrong. And so sort of at R500, you can see that you're slightly higher than the observed median value. And this is because basically AGN feedback at high redshift isn't doing enough work. So this is, clusters the potential of clusters is too deep for you to be able to kick any gas out at low redshift. So you need to do all of this work at sort of redshift, sort of 4, redshift 2, in that kind of range. And in this case, we're removing gas from the cluster, but it's not being removed from the sort of potential as it collapses. And so then that gas falls back in, and so you get a much higher, you get a higher gas fraction and a weird shape at the start at R500 for the cluster. And then in the core, we can see that we've got too much gas. So the injet just shows the same thing, but on a log-log plot to emphasize that we are sort of underestimating the central density by about a factor of 3. And this is because basically at low redshift, the AGN feedback is too effective and too active. And so basically it's injecting too much entropy into the center of the cluster, so your gas fractions are too low. And this isn't limited to illustrious TNG. The cluster Eagle simulations and the Fable simulations that came out recently show the exact same effect. And actually in the Fable simulations, excuse me, there's a very detailed explanation into how all of the simulations basically can't get this right. But it's interesting to note that if you say you take the Eagle model, for example, and you just increase the mass of the particle, so you decrease the resolution of the simulation, you suddenly start getting the gas fractions, and the cool core fractions suddenly start to look better as well. So this sort of effective AGN model that most simulations use works if you're sort of at 10 to the 8 solar mass resolution, but when you start coming down to 10 to the 6 so that you can start resolving the galaxies, all of a sudden your AGN feedback model no longer works. And so this leads to the question, well, what's missing from simulations? So most simulations only include the physics they have to, right? So hydrodynamical, cosmological simulations are very expensive. And they only sort of simulate the physics to get the sort of broad galaxy and sort of hot halo properties correct for most clusters. And so, you know, there are other physical processes that are just simply not included in these simulations. And so one of these is cosmic rays, and this is an active area, and there's a lot of exciting research coming out on that, but I'm not going to cover that here. There's also heat transport. So the isotropic case of heat transport has been covered many times. The actual conductivity coefficient is sort of uncertain, although there's work by Max Gaspari that shows it should be very, very low, otherwise your cluster's far too sort of smooth compared to observations. And the other option is that we just simply aren't doing our AGN feedback model well enough. And so you can have other effects going on, like radiation, for example. But I'm going to come back to heat transport, because if you look at this picture of the toothbrush relic from observations, so what you've got here, basically, the blue, which is quite hard to see, is the mass distribution from weak lensing. The purple in the middle is just basically X-ray emission from hot gas. And then the green is the interesting thing here, which is basically radio relic. So it's radio emission. So this tells you there's two things here. It tells you there's relativistic electrons that get there somehow, and that's still up for debate. But it also tells you there are magnetic fields there. And the moment you have magnetic fields, the isotropic case of heat transport is no longer correct. And so you have to go to the anisotropic case. And luckily, Raoul Kanan has actually got anisotropic thermal conduction working in our simulation code of repo. And so we actually now run 12 clusters with and without anisotropic thermal conduction. I should note that we're using the full Spitzer value here for the conduction, but we don't actually know what that should be. But there's work by another postdoc at MIT, Hoi Li, who hopefully at some point will have a paper on this, although it's a bit stuck in technical difficulties right now. And so what we can do is the same process again. We can look at the cool cores in these 12 clusters with and without anisotropic thermal conduction. And so you saw this plot before. It's the various 6 criteria as before, but now the blue squares are without thermal conduction, and the red triangles are with it, and then the grey lines just match up the pairs of clusters with and without thermal conduction. And so you can see that thermal conduction makes a difference depending on which criteria you pick and which cluster you're in. So for example, this cluster here is our most massive one, and you can see that in the density in the center, it makes a density gradient, it makes a big difference. But actually, if you go to the central entropy excess, it makes very little difference. And in some cases, it actually goes the other way, for example, for this cluster here. And then there's this one here, but it has a timing issue, for example, because the mass isn't quite identical. But you can see that the general effect overall actually is to increase the cool-core fractions in these simulations. And so that's basically shown in the small panels on the right. The solid blue line is the median sort of cool-core value for this particular criteria. And you can see that basically in all of them it sort of trends towards cool-core clusters. Sorry?
The cooling time looks like it's longer for the...
Oh, right. So in all cases, cool cores appear at the top, so it's always flipped. So the shorter cooling time is at the top. Yeah. Sorry. Yeah. Sorry. Yeah. So in all cases, cool cores would appear at the top. So for the cooling time and for the central entropy excess, the axes are flipped. So cool cores always at the top. So yeah. So the clusters go from say the longest ones are sort of 10 gigayears, and they go to sort of 3 or 4 gigayears in some cases. So that, yeah, if you go up, then you're going to shorter cooling times on the central plot. And so this is an interesting effect, and you can have a look at what it does to the redshift evolution of the cool-core fraction. And so this is just simply the difference between the cool-core fraction without and with thermal conduction. And so you can see at high redshift, you actually get fewer cool cores when you have thermal conduction, which is something we don't quite understand yet and we're still looking at. But at late times, at low redshift, you get more cool cores. And that's just a product of the thermal conduction. And when you sort of look, so we only have 12 clusters here, so we can't really do a statistical study of the redshift evolution. But you can take this correction factor and you can apply it to the TNG simulations that we had where we've got hundreds of clusters, and you get the following. And so here, the sort of cyan dashed line is the previous result from illustrious TNG. And then if you correct that with the anisotropic thermal conduction that we saw, then you get a much flatter redshift evolution. And so you can see, for example, for the cuspiness parameter, that's now actually a reasonable fit to the data. And you can see for the central cooling time, it's much closer to the observations. It doesn't work in all cases. So you still get a flatter evolution here, but you're now over-predicting the cool core fraction for the central density. So again, this does depend on the cool core criteria you're picking, but anisotropic thermal conduction does seem to have some impact here. And so the question is, why does this give you sort of a better match to the observations? And again, it's all about AGN feedback. And so what I'm plotting here is basically the energy injected by the central black hole in the simulation. So we find it at low redshift 0, and then we just track it back through time through the simulation. And so here the solid lines are the total energy injected by the black hole. So the blue line is the median for without thermal conduction, and the red line is with thermal conduction. This dashed line here, again, is the blue and red are conduction and no conduction. And you see that basically that doesn't change. And then you go to the kinetic mode here, which is basically the radio mode. So this is the sort of one that does the maintenance once the cluster's formed. And you can see now that you have this difference. So this is about a 25% drop at redshift 0. And here I'm just showing underneath, I'm just showing basically the radiative losses. So if you take all the gas within R500 and calculate its cooling rate, then that's basically the amount of energy you would expect it to lose over that time. And so you can see that doesn't really change with anisotropic thermal conduction included. And so basically what this tells you is that the efficiency with which the AGN feedback is mixing with the ICM is higher. And so that's what's shown here. So basically now what I'm doing is just taking the ratio of those cooling losses and the AGN energy and total AGN energy injected. And this time I'm measuring the cooling within 0.15 R500, so the traditional definition of a cluster core, and within the complete R500 volume of the cluster. And you can see that when you include thermal conduction, you actually see an increase basically in the efficiency with which the AGN is interacting with the ICM. And if you just basically then take the difference between with and without conduction, then you get this plot here. So this is noisy, but you can see that basically at late times, the AGN feedback is actually more efficient, and it seems to be more efficient, again, if you go into a smaller radii. But again, we only have 12 clusters, so there's not great statistics here. And then actually at high redshift, there's an interesting case that maybe actually the AGN is less efficient when you have anisotropic thermal conduction. And the reason that all of this is why the AGN feedback is more efficient is because anisotropic thermal conduction makes the ICM unstable to basically perturbations. And so every time you have a perturbation, like an AGN feedback event, then you create a lot of mixing in the ICM. And so because you have higher mixing, then the energy is more easily transferred and coupled to the ICM, so it heats it more easily, and so you actually need less energy to achieve self-regulation in the black hole. And so I'll finish with my conclusions. So let's just TNG gives you a big sample of clusters. Their integrated properties are a reasonable match. And there'll be a paper by a student from CFA that'll show that soon, hopefully. But the exact structure of the hot gas, when you go from integrated properties to actually looking at sort of thermal structure of the ICM, isn't perfect. And it remains a challenge for numerical simulations. However, there are additional physical processes like anisotropic thermal conduction that you can include that will help you reproduce the ICM better. Thank you.
You mentioned that illustrious CAG uses large sample classes whose integrated properties are reasonable and realistic. But I mean, how many parameters do you set, and how do you generally decide state?
Yeah, so this is always the case. So for illustrious TNG, so I'm not part of the core team, so I wasn't privy to their exact calibrations because I was working with Eagle during that time, the competitors. But basically, yeah, there are a set of parameters mainly on the amount of sort of supernova feedback that couples and the amount of AGN feedback that couples to the surrounding gas that you tune to get that right. But for illustrious TNG, basically they took, I think, about 5 or 6 key relations, and so tune the simulations on those. They only tune them for the 100 resolution, and then they ran the simulations. And so there are 6, 7 relations maybe that are basically reproduced because the model says so, but the rest are predictions of the model. And so, for example, cool cores was something that just wasn't looked at here.
Do you know how strong the effect of the anisotropic nature of conduction is? I mean, like, was there ever any time that you looked at, conduction that was isotropic?
Yeah, so conduction as isotropic has been covered already quite extensively in the literature by people like Max Gaspari, for example, has a paper in 2013 on this. And so, yeah, if that is a very strong effect, if you use the full sort of Spitzer coefficient for the conduction. But it's not clear what happens when you go to the anisotropic case. So as I said, there's a postdoc at MIT, Hoi Lee, who is looking at this right now. And so whilst full Spitzer is sort of basically the most optimistic effect, we don't actually know what the value should be. So it's a study that will hopefully come out soon.
Any other questions? Please.
So when you use the undead sample, like which sample do you use? Do you use the ESZ sample or the X-ray flux unit sample?
So I'll just go back through. So when I'm, for example, plotting this one here, so if we're using central, hang on, let me remember. If we're not using the cooling time or the central entropy excess, then we're always using SZ samples, all the way from redshift 0 all the way to redshift 1 or 2.
But my question is, in this paper we have 2 samples that we measure the fracture forward in 2 samples.
Oh, we're always using the SC sample. We're always using the Planck sample. Yeah, where possible, we're trying to use unbiased samples, so Planck or SPT. It happens to be for the central cooling time that there isn't really measurements, for example, at low redshift for that. And so then we have to use the X-ray data.
So the sample is the SE sample?
Yeah.
But at low redshift, which is less than some Z equals?
Yeah, so for SPT, they have measurements of every criteria that we use. And so we're always using SZ above redshift 0.25. It's only at low redshift for cooling time and central entropy that we're using any X-ray data. And that's basically because they don't exist there.
Below 0.25?
Yeah. Yeah.
Let's thank David now, please.